So I guess this is what, 7:30 part 2. So let me sort of motivate it this way. So suppose I have this integral. And just for the sake of being a little more simplistic, suppose it's an indefinite integral. And I want to know what function's derivative is 3x plus 5 to the 10th. Now, you might be able to guess and check for a while what the derivative is, but that is not any sort of useful strategy. You don't want to guess and check at things unless you have no other choice. And it turns out that we don't necessarily always have to guess and check. What we can do oftentimes is we can develop some systematic ways of doing things. And so if, you know, for the sake of brevity, if we look at this thing and we say, okay, interesting, I know the antiderivative of 3x plus 5 because it's just a polynomial. The formula we talked about 20 minutes ago will work for that. And then you know the antiderivative of power 10, you know. So let's just make this clear. So we know the integral of x to the 10th dx. Look, again, let's think about these simple rules. This would be x to the 11th over 11 plus c. And we also should know this, which would become 3x squared over 2 plus 5x plus c. So when I say we know, you're going to say, well, I don't know that right now. I get it. But what I'm telling you is these rules for these two integrals are, you could see the pattern. I hope you see the pattern at least. And if you don't right now, I hope you spend some time later to see the pattern. But what we're looking for, is there a similar pattern for the original integral, or is there somehow we can use this knowledge to help us with the original integral? So the composition this is a composition. This suggests that we might simplify if, or maybe not, or simplify, or reduce to an easier integral if we look at the chain rule. The chain rule was our way of differentiating the composition. So maybe it can help us get out of this problem of integrating a composition. So what I mean by that is we do the following. So to differentiate 3x plus 5 to the 10th, what did we do? Well, we differentiated the outside, left the inside alone, and then let me write it. To differentiate this, what we did is, let's not write it that way. That sounds silly. So let's write it like this. The derivative of this is this. So can we reverse it? in a systematic way. That's what we want you to think about. And it turns out we can. So one way to do this is to make a substitution, or substitute a new variable. So let's do that on the next page. So actually, before we do that, let's think of this more. So we want to come up with some pattern, some systematic way of reversing compositions. So more specifically, reversing the chain rule of a composition. And so one idea is to substitute a new variable. So let us show you how this might work. And then what we're going to do is we do it, and then we say, how do we know it's legal? And it turns out that it's legal by the chain rule, but it's also can be thought of as legal because you can check your answer. So let's go back to our original problem, which was 3x plus 5 to the 10th. So what I'm going to do is I'm going to set a new variable. So I'm going to say y is 3x plus 5. And so a first attempt you might have is you might say, okay, great, then this is just equal to the integral of y to the 10th. But the problem is we're leaving the universes of x. So we can't just replace x with a new letter, y. We also have to understand that that changes this dx. So let's just, for the sake of it, say since we're getting rid of x altogether, we have to remove dx as well. So what we need to know is, how is dx and dy related? Well, we have a relationship. Over here, we know that dy dx is equal to 3. Now, if we use some cheating, if we just cheat for a little bit, let's pretend that this is a fraction. So pretend dy dx is a fraction. And we do that so that we can write dx is equal to 1/3 dy. So that means then that I can come up here and I can replace dx with my dy. But it's, excuse me, replace dx, but what's dx equal to? It's equal to 1/3 dy. Now, you might say, why did I bring that 1/3 out front? Well, remember, the integral, as I've written it, this indefinite integral, it's only interested in worrying about the variables. So anything that's not a variable can come outside. Just like when you were taking derivatives, you didn't have, the constants could come out. And what's nice about this, what we just did, is now this is an integral where the pattern is not difficult. What's the integral? Well, it's y to the 11th over 11. And then, of course, we have to put this plus c because who knows, there's many of them. And another way to write this is 1 over 33 times y to the 11th plus c. And then the last thing we want to do is we started in x, and it would be a bad idea if we gave you one currency and we gave the answer in another currency. So what we'd like to do is we'd like to go back to our original variable, and that would be replacing y with 3x plus 5. And so what we've done, we think, if it's legal, is we've computed this indefinite integral. by first reducing it to a quote-unquote easier integral using a substitution. All right, does anybody have a question about this?
So for dx.
Anybody have a comment? Question? So the thing is, if you're a student of calculus, you might say, how is that legal? Because if you paid attention to what we've been doing, you're going to say dy dx, this is just notation. You might say, how is it legal to do this? Well, it turns out it is legal, and it's a big theorem called the change of variables theorem. And it's really nothing more than the chain rule in disguise. So really what this thing is, what we did is we took the derivative rule, the chain rule, and we rewrote it in the notation or the language of integrals. Does anybody have a question about this? So let's look at another example. Actually, I guess we should be, let's clean up. So so the above calculation or the above work is logically sound. And so it's called the substitution rule, or more famously, it's called the change of variables. For integration. So it basically says this. It says the following. Let u equal some function g of x.
Yes, u.
Then the integral of f composed with g times g prime d of x. This is equal to the integral of f of u du. Now look, I'm going to be completely honest with you guys. For most students in Calculus 1 and Calculus 2, this is a very complex formula to understand. Most of you will not understand this formula right away, even though you'll be able to compute integrals. So perhaps the best way to learn it is to not try to memorize it. It might even be to ignore the rule, and it might just to be practice doing substitutions. And that's what we're going to do right now. So please, at any time, if you have a question, stop and ask me. So let's integrate this expression. What is the antiderivative of the square root of 5x plus 2, 3 dx? So what we're going to do is it's going to be very similar to the last problem. We're going to set a new variable. Let's use u this time. U is 5x plus 2, 3. And then the derivative of u with respect to x is 5. So if we replace these old variables with their new ones, we get the square root of u, and then our dx is 1/5 du. And then, of course, how do you integrate this? Well, I would encourage you to rewrite it as u to the 1/2. And so that becomes u to the 3/2 divided by 3/2.
2/3.
And of course, now if you divide by 3/2, that's the same as multiplying by 2/3. So I would write this as 2/15 u to the 3/2. plus c, and then last but not least, you can put your original variables in. And you get 2/15 times the quantity 5x plus 23 to the 3/2 plus your arbitrary constant. Once again, if you take this answer in the bottom right and you compute the derivative correctly, you will get what we started with. Does anybody have a question? Comment? All right, so let's do another one that will help you with your homework. Let's take this integral. How about 1 over 1 plus 25x squared? So one option here is to recognize, you might say to yourself, this looks a little familiar, but it's not completely familiar. But if you make a correct or a cute little move to it, something that's familiar. So in particular, if I replace 5x with y, so let me say y is equal to 5x. Now, why would I say 5x? Well, what happens if I do that is if y is equal to 5x, then this integral becomes 1/5 the integral of 1 over 1 plus y squared dy. And it becomes that because dy dx is equal to 5. Now, why would I want to make it look like this? Well, I want to make it look like this because I remember my derivative rules, and I know that the derivative of the arctan is 1 over 1 plus input squared. And so all that remains is to plug the original variable back in, and I've computed this particular integral. Does anybody have a question about this, a comment? Going once, going twice. All right, what else? Do you guys have any questions about the exam or any of the homework problems that I can give you hints on or get you started with while we're here? Or any questions about anything, any concerns? Anybody? Going once? Going twice? You sure? All right, well, if that's it, then I will say thank you for joining. Again, I'm free. If you have any questions that you need answered for the exam, for example, you know, I'll do my best to respond to anything today and tomorrow in a timely manner. But the sooner you get it to me, the better, because you have a better chance of me being able to answer it. So, okay, any other questions, comments? Well, listen, thank you guys. I appreciate it. It was, well, I don't know if it was a good semester. I mean, it's kind of hard to judge how things go here, especially since we threw this together. I shouldn't say threw it together. You know, it's hard to plan an online, virtual, hybrid thing in a couple weeks. So obviously things could have been much better, but hopefully you got something out of it. Hopefully you'll, you know, I can make things better if we have to continue in this manner going forward. But I do appreciate you guys understanding and giving a good effort. So best of luck to you if I do not hear from you guys again. Thank you very much. And good luck on any other exams and school this fall. Hopefully things get better sooner than later. All right. Well, if you have questions, shoot me an email. Otherwise, take care, guys. Good luck. I appreciate it. Thank you.